So let's look at the equation of CONH3,5Ln+. In this reaction, we are replacing L with water. A number of different anionic ligands were looked at for this process. And once again, we are looking at, this time on the x-axis, we're looking at the log of the rate constant. The more negative the rate constant, the more negative the log of the rate constant, the slower the reaction. The more positive the rate constant, the faster the reaction. We're looking at that as a function of the log of the equilibrium constant. If the equilibrium constant, the log of the equilibrium constant is negative, you have very weak metal-ligand bonds. If the log of the equilibrium constant is greater than 0, you have strong ML bonds. Notice that the nature of the ligand, or the type of ligand used, depends upon how fast the reaction occurs. If you have weak metal-ligand bonds, like the bond between cobalt and NO3-, you have a very fast rate of reaction. If you have many of the bigger halides, I-, Br-, and Cl-, those bonds are weak, so the reaction occurs faster. As you get stronger bonds, such as with F- or NCS-, the reaction goes slower because the bonds between the metal and the ligand that is leaving is stronger. The conclusion you can draw from this data is that the stronger the metal-ligand bond, the ligand that is leaving the complex, the slower the reaction rate. This is consistent with the dissociative mechanism. So let's talk about the equation of CONH3,5Ln+. This linear correlation between the log of the equilibrium constant and the log of the rate constant shows there's a correlation between the cobalt ligand bond strength and the ability of the ligand to leave the complex. This also suggests that the mechanism for substitution of the displacement of a ligand by a water molecule occurs by the dissociative mechanism. So we've looked at isotopic exchange of water. That occurs by a dissociative mechanism. We've looked at aquation and annation reactions. Both also occur by dissociative mechanisms. That suggests that that many substitution reactions occur by a dissociative mechanism. Let's look at some additional data that may help us decide if dissociation is truly the way that substitution reactions occur. Let's look at reactions between coordination compounds with bulky ligands, such as chelating agents, and replacing either water or another ligand like Cl-. So when we take a coordination compound like this substituted ethylene diamine that's bonded to the CO3+, and 2Cl- is bonded to the CO3+, and react it with water, for an associative rate determining step, remember we're going to form a 7-coordinate complex, so water must bond, and one of the Cl's must still be bonding but is going to leave. For the dissociative step, we end up losing Cl- to form a 5-coordinate complex. These are the two different mechanisms. Once again, you've seen this before, but we're going to see how ligand bulk affects the equation of coordination compounds. Here we are looking at the rate constants for the equation of trans-bis substituted ethylene diamine dichlorocobalt-3 complexes. This is the reaction that we were looking at on the previous slide. Now notice that when we look at this table, R1 and R2 are the organic groups bonded to the different disubstituted ethylene diamines. R3 and R4 are for the second disubstituted ethylene diamine. What you'll notice as you increase the bulk of the bidentate ligands, if you look at the rate constant, you also increase the rate of the reaction. This means that there's some crowding. There's steric crowding around the metal cation. And what needs to happen is that the chlorine is not as tightly bonded to the cobalt because it has these bulky rings that keep pushing it out. This is also consistent with the dissociative mechanism. There's one final piece of evidence that we must consider when we decide if it's a dissociative or associative mechanism. It looks like that we have a dissociative mechanism from all the data I presented thus far. But let's look at two more reactions. Let's look at CONH35Cl2 2+ plus water. And the Cl will be replaced by H2O. The rate constant for that reaction is 6.7 times 10 to the minus 6 per second. Now, if we also look at the disubstitute or the dichloro compound, you'll notice that to replace one water, the reaction occurs at a much faster pace. Since the second reaction with two chlorines bonded to the original coordination complex goes faster than the first, you need to decide, is this consistent with the dissociative or an associative mechanism? It's consistent with the dissociative mechanism because the greater amount of charge on the coordination complex, the more difficult it is to remove the Cl- ligand. K should be smaller. If it's for the associative mechanism, the greater the charge, the more the attraction between the water and the complex. K should be larger. So which is correct to you, the dissociative mechanism or the associative mechanism? This clearly supports the dissociative mechanism. So, the mechanism for substitution reactions are supported by dissociative mechanisms. All the data says it's dissociative. The rate determining step is based upon the strength of the metal-ligand bond. The strength of this bond depends upon the metal cation's charge density. Remember that the larger the charge density, the harder it is to break that metal-ligand bond and the slower that the reaction will proceed.